Hello there. The television tape recorder is undoubtedly the most complex piece of equipment normally employed in a television broadcast studio. I believe it's worth our while to learn something about these machines, not only because they have become important basic tools in the broadcast industry, but also because they illustrate the practical application of a great variety of advanced electronics techniques. The objective of a television tape recorder is almost self-evident. It is to record complete television programs, both picture and sound, on magnetic tape. Now, the tape employed is basically very similar to the familiar audio tape, quarter-inch wide, used in the both professional and home style of audio recorders. However, there's an important difference in the tape used with these large television tape recorders. The tape itself is considerably wider. It's 2 inches wide. It is, however, deposited in the form of an oxide coating on mylar, very much like audio tape. Now, because the problem of impressing television signals on tape is considerably more complex, we find that a very complex pattern is required on the tape itself. The information is recorded in the form of a series of tracks, as you see indicated in this little sketch. This shows the 2-inch width of the tape. You'll note that a control track is laid down across the upper edge of the tape. An audio track is found across the lower edge, as it's portrayed in this sketch. And the video information is deposited in the form of a series of transverse tracks extending across the width of the tape. These are nominally 10 mils or thousandths of an inch wide and are separated by guard bands of about 5.6 mils. There is also an additional audio track known as the Q track, which is adjacent to the control track along the upper edge of the tape, as you see it here. The reason for employing this basic transverse scanning technique is to obtain the very high writing speeds that are needed to record the high bandwidth video signals. Let's take a look at some of the mechanical aspects of the television tape recorder as we begin our exploration as to how it works. Much of what you see here on the tape transport panel is self-evident. Here's a supply reel and a take-up reel down immediately below it. We can trace out the path of the tape quite readily. As it leaves the supply reel, it first passes a stabilizing arm, which controls the tension on the tape as it passes through the active portion of the machine. The tape then passes over an air-lubricated guide. Air under slight pressure is forced under a series of holes in the upper surface of this guide so that the tape literally floats past on a cushion of air. Next, the tape is passed by a master erase head, which serves to clean off any signal that might previously have been recorded on the tape. This is used, of course, only in the record mode of operation. Within this housing is located the basic video headwheel assembly, where the transverse scanning is accomplished that records the video information on the tape. Behind this little plastic cover right here is the actual video headwheel, a set of 4 heads which are mounted in the rim of a wheel approximately 2 inches in diameter. We'll see some close-up views of this this part of the system a little bit later. For the moment, let's simply note that the tape is cupped by the action of a metal guide that you see in this region here, so that it conforms to the circumference of this rotating head wheel where the video recording actually takes place. The tape then emerges from this housing and passes along to a cluster of heads associated with the audio and cue channels. You may be able to observe 2 posts that bear against the tape, against the oxide surface of the tape in about this location right here. The first of these contains a pair of erase heads that erase narrow stripes along the appropriate regions of the tape near the 2 edges. And the following post then is the audio and cue record head, where audio or cue information is recorded in the appropriate tracks. Next, we encounter the capstan, where the driving force is imparted to the tape. In normal service, of course, the pinch roller that you see right here would be jammed against the capstan to exert a grip on the tape. Then we encounter a counting capstan, which is mechanically coupled to an elapsed time meter, which is in this area right here to enable an operator to keep track of where he is on a reel of tape. Finally, another stabilizing arm, and the tape is wound up on a take-up reel. Well, the basic mechanical arrangement, you'll note, is not very different from what you will encounter in an audio recorder, with the very important exception that this video headwheel assembly is needed in order to record the very important video information. Now, let's take a look at one of these video headwheel panels that has been removed from a television tape recorder so that we can see some of its important details a little more readily. I have such a headwheel panel over in this area here that's been removed from the panel and laid down horizontally. Normally the tape would pass through in this area right here, be cupped by this vacuum guide to conform to the circumference of the headwheel that you see in this location right here. Now, one of the details that you can see quite readily in this particular view is the cluster of brushes and slip rings right in this area right here, which are used to conduct signals to and from the rotating heads. You'll notice a total of 5 of these brush and slip ring assemblies. There's one for each of the 4 head channels, plus a common return for the 4 heads themselves. Now, the heads are mounted around the rim of this wheel, which, as I indicated, is roughly 2 inches in diameter. They're a little difficult to see in this kind of a view, but I think perhaps you can make out one right under the pencil point right here. 90 degrees later along the wheel, there's a second head, a third one, and a 4th head. 4 heads mounted around the circumference of this rotating wheel. Now, down at the other end of the motor shaft, this obviously is the motor which drives the head wheel, you'll find a little magnetic tone wheel. This is nothing more than a metal disc with one tiny notch in its periphery. You can see it at this point right here. This tone wheel, of course, makes 1 revolution for each revolution of the head wheel, since it's directly coupled to the same shaft, and it rotates very close, not quite touching, but very close to a magnetic pickup head in this region right here. So a little pulse signal is generated every time the video head wheel makes exactly 1 revolution. Now, one other very important aspect of the video head wheel panel is the vacuum guide, which can be released and swung back from the head wheel, as I am now doing. Here you see the inner curved surface, which causes the tape to be cupped so that it does conform to the circumference of the wheel. There's vacuum applied through some grooves in this guide by means of a little hose that you see extending off in this direction here. And there's also a control track head mounted on the guide assembly, mounted in such a way that it bears against the oxide surface of the tape, the inner surface of the tape, to lay down a control track, whose function we'll discuss a little bit later, almost immediately after the video information has been recorded as the heads move past the tape in this general area right here. Now, again, as we'll see a little later, the precise positioning of this vacuum guide is very important. It's important that the dimensions associated with the playback process be virtually identical to those associated with the recording process, or there will be geometric distortions in the final picture. Well, that, I think, gives us some impression of one of the key mechanical components in the television tape recorder. We might now consider a little bit about the electronic circuits. In the lower part of the machine, there are banks of modules containing transistorized circuits associated with the electronic part of the machine to provide suitable record currents and to amplify the playback signals from the actual audio and video recording heads, and also to provide appropriate driving power for the several motors associated with the transport. Before we examine any of these modules in detail, I think it would be worthwhile to look at a block diagram of the basic video recording system for this type of machine. Such a block diagram is displayed over here on the easel. The video signal is enough more complex relative to an audio signal that it's necessary to employ a great deal of processing in the process of putting it on the tape and getting it back off. The video signal, as it's first brought into the machine, is first impressed on an FM carrier. So the signal that is actually recorded on the tape is not the original video signal, but is actually an FM wave. This gets around certain serious limitations in the recording medium with respect to basic linearity. The FM signal is passed through a group of 4 record amplifiers which provide currents for the 4 video heads mounted in the head wheel. The connections to the video heads are brought in through slip rings and brushes. As you see indicated in this area up here, there is a record playback relay, or the equivalent, that enables the set of heads to be switched between the record and the playback modes. Now, for the process of playback, the same heads are used to generate signal currents, which are brought into a 4-channel set of playback amplifiers and equalizers. It's necessary to adjust the frequency response in a number of respects and equalize the signals generally to preserve good signal quality. Then, because there are 4 head channels, but we want only one signal at the output of the recorder, it's necessary to employ a group of switching circuits which transform the 4 head channels into a single FM signal, which is then applied to the demodulator, which in turn recovers the video signal. Now, the video signal, as it emerges from the demodulator in a tape recorder, is not of particularly high quality. It is contaminated by switching transients, by some of the distortion which is inevitable in the processing to which it's been subjected. So the signal is passed through a processing amplifier which is capable of cleaning up some portions of the television signal. In particular, the sync and blanking signals, which are highly standardized, can be regenerated almost completely. If the machine is then employed for color television recording and playback, there would be a set of color stabilization circuits which perform further operations on the signals before the signal is finally delivered to the outside world. Now, in a monochrome type of machine, the circuits that you see outlined in the dotted lines here may not be required. Most practical television tape recorders are so designed that they can be used optionally for either monochrome or color recording. Well, with that much background on some of the theoretical considerations involved in the record and playback process, let's examine some of the actual circuit modules as they are employed in this particular type of machine. Over in this panel on the left, we have a number of the modules or amplifiers associated with the recording process. The program audio, for example, is introduced to the machine through this module right here, which provides the driving current for the audio heads. Here we have a video input module, immediately followed by a modulator where the FM signal is first produced. Then we have a group of 4 identical recording amplifiers which further refine the FM signal and adjust its level appropriately to meet the requirements of each of the individual heads. I think it might be instructive if we withdraw one of these modules to give you some impression of the physical construction that's been employed in this particular type of machine. Here we have, this happens to be one of the video record amplifiers, and you can get some impression of the manner in which this type of transistorized circuitry is designed. The transistors themselves are not mounted in sockets, but are directly soldered into the circuit. You may be able to pick out a number of them down in this area here, and there are some large power transistors associated with the actual driving of the video heads up in this area up here. You'll note that rather conventional components are used in this particular type of equipment, but the layout is designed for easy serviceability and easy troubleshooting. Down in the forward end of this module assembly, you'll see some of the switches and potentiometers associated with the control functions. There happens to be a video delay line that actually delays the FM signal in this case, associated with this module, a number of transistors and other small components. One of the standard features provided with a machine of this sort to make it easy for the customer to use is a module extender, which will enable any one of these modules to be operated in its withdrawn position, about as you see here, for ease in troubleshooting. Well, let's restore this into its normal position and direct our attention over to the second module bank immediately under the transport. Here we have circuits that are associated with the video playback function. There's a group of 4 identical video playback amplifiers which again amplify the FM signals recovered from the 4 heads. Then there's an FM switcher which transforms the 4 channels down into one by switching at the appropriate instant so that a single continuous signal emerges from this switcher module. Then there is a limiter which gets rid of all level variations in the FM signal recovered from the tape, a demodulator which recovers the video signal, and then a rather complex group of circuit modules associated with the processing amplifier function. The process of regenerating the signal is actually one of the more complex processes in the machine. It's necessary to employ a number of AFC systems and pulse counting circuits and the like to regenerate the sync and blanking components of the signal. Now, most of the other modules that you see here are associated with the servo systems that are required in the tape recorder. The tape recorder requires a minimum of 2 servo systems, and some versions of the machine actually employ a grand total of 3 to control certain important aspects in the mechanical operation of the machine. There is one servo system that controls the speed and the phase of the rotating head wheel assembly. There is another one that controls the speed of the capstan, which in turn controls the speed with which tape is pulled through the machine. This is necessary, of course, in order to make it possible for the video heads in the playback process to track accurately across these transverse tracks as they're laid down across the width of the tape. And finally, in some machines, it doesn't happen to be characteristic of this particular model, there is a servo system, an automatic control system, which establishes very precisely the position of the vacuum guide which pushes the tape up against the rotating head wheel. In this particular machine, there's only a mechanical, a manual adjustment for that purpose, but there are some electronic correction circuits that operate on the final signal to give very much the same overall effect as if there were a mechanical automatic control system. Well, with that much introduction to the overall concept of the machine, I think it might be appropriate to conduct just a bit of a demonstration to show some parts of the machine in actual operation. In general, the record and playback functions are slightly separated on the machine in order to minimize the chance that an operator will make an error by pushing a record button, so to speak, when a good tape is mounted on the machine. In general, the controls you see associated with this panel right here are those that are used for playback. Those that are associated with the record function are located somewhat separately over on the opposite side of the machine. So, as I say, to minimize the possibility of making any kind of an operational error. There are a lot of convenience features provided in a machine of this sort to fit the requirements of the broadcast industry. For example, there's a rather complete group of switches here for monitoring various signals at strategic points in the machine. The upper row of button controls the display on a picture monitor. The lower row of buttons is associated with a built-in waveform monitor or oscilloscope, which is an important accessory or important item in the overall machine. There are also little features like the microphone mounted in a retractable holder here, which enables an operator very readily to add identifying information or speak audio notes, if you will, to be applied to the cue track in the machine for identification of recordings or recording of any particular technical difficulties that might have been encountered and that type of thing. Now, returning to the basic transport panel, let me indicate what a few of the basic functions are. As you might expect, there is one button that is marked play, and in normal operation, the only action necessary to activate the recorder once a recorded tape has been properly loaded on the transport is to depress the play button. However, there are additional facilities associated with the transport. I just pressed the stop button, obviously, there. There is a standby mode, which puts the recorder in a mode that is very much like play, except that the pinch roller is not energized, so the tape is not actually placed in motion. However, the motors are brought up to speed. All other circuits are in normal operating condition, and it's possible to check out a number of important details of machine operation in this particular mode. There are also modes called wind. Forward wind, which, as its name implies, gives you a fast forward action, and reverse wind. The machine comes to a stop and, as you see, speeds up in the opposite direction. By jockeying these two switches around and noting the reading on the tape timer, it is possible for an operator to rather quickly locate any desired segment in the tape or to rewind the tape rather quickly after a recording is complete. Now let's place the machine in the playback mode. While we were preparing for this little demonstration, we recorded several minutes of a color bar signal that appears on the picture monitor very much like a grayscale in order to just give us a signal that will enable us to demonstrate several important aspects of the machine operation. One of the controls down here on the control panel is one marked control track phase. This controls the relative timing with which the capstan pulls the tape through the machine. There's a meter located immediately above it on which one tunes for a maximum, so to speak. You adjust this control track phase so as to get a maximum reading on this meter. This means that you are pulling tape in just the right phase so that each video head is passing directly over one of the tracks on the tape. Now, there are 4 possible positions for this control track phase knob. Since the head number 1 on the video head wheel can be made to scan the tracks that were produced by head number 1, 2, 3, or 4. This is really controlling the operation of the capstan servo system. Now, we can see a number of other interesting details of machine operation if we direct our attention to the picture monitor. One of the important characteristics of this type of machine is that the information in the video signal is recorded in sequence by a series of heads. The relative speed of the heads compared to the frequency of the television signal is such that a band of approximately 16 lines in the television signal is reproduced by each head before it is moved along and another head moves in to take its place. Now, if we deliberately disable one of the head channels, you get the sort of effect shown here, where you notice that roughly 1/4 of the picture breaks up. You have nothing but a noise band indicating that one of the 4 head channels has been removed. You notice also that the synchronizing information becomes unstable because of the missing 16-line bands. But the amount that we are removing from this image here corresponds to the amount of information that is scanned by each head in the system. It is quite easy to see the contribution of each head in the system by examining some of the key waveforms that are associated with the machine. This built-in waveform monitor enables us to see some of the basic signals. What we're looking at here is the final video output from the machine producing the signal that you just saw displayed on the kinescope. If this is the signal after it has emerged from the processing amplifier, and you can notice that the synchronizing pulse and the blanking interval are displayed in rather clean fashion. As a matter of fact, there is an expand facility built into the waveform monitor that enables us to see that sync and blanking pulse very clearly, and you see that it is quite clean with very little crosstalk or other contaminating signals in this region. However, if we look at the signal just as it comes out of the demodulator, we find something rather different about the character of the signal. Now there is a great deal of residual noise on the synchronizing pulse. This happened to have been a color signal, so there's the remains of a burst appearing over here in the back porch area. Again, we can see this in a little bit more detail if we enlarge the waveform. But after passing through the processing amplifier, this signal is rather completely cleaned up, giving you the same effect that we observed a moment ago. This is, of course, a horizontal rate display. This is one line from here to here, another line from here to here. Now, another waveform monitoring facility provided in the machine is the output of the FM switcher. Here you see a display showing the FM signal. One of the significant things about this is that you can identify the contributions of each of the head channels. As a matter of fact, if I deliberately lower the level of one of the channels, you'll see the waveform reduce in amplitude in one part of the display. It's also significant that this level is not particularly stable. If you notice carefully, you see it sort of bobbling around. This is an indication that the capstan servo is doing its job in holding the head centered over the tape. The minute it starts to move off the track just a little bit, the head moves off the track, the capstan servo operates to correct it so that the maximum level of signal tends to be preserved at all times. But you see the little bit of residual variation that is more or less intrinsic in the tape recording medium. In order to monitor the operation of the servo systems, there is a special display provided which enables one to see some of the key waveforms. I'm afraid the details don't show up at all well in the display that we're seeing here, but there are displays shown that enable an operator to see quite readily exactly in what condition the capstan servo is operating. You can also check for the continuity or the presence of the various pulses associated with the head wheel servo system as well. One other important aspect of the machine that I'd like to demonstrate is the significance of the positioning of this vacuum guide. I've mentioned several times that it's very important that the guide be positioned accurately if you're going to avoid geometric errors in the image. To show why that is, I can deliberately misadjust the vacuum guide with a little adjustment here, and if you can get a view of the waveform monitor, I see that I've just gone past the point where the recording was made, so I'll have to back up the tape for just a moment here in order to recover the signal that I need to demonstrate this particular effect. I picked up about 30 seconds. I now need, oh, that gives me about a minute of tape if I stop it there. Now if I put it back in the play mode and wait just a moment for the signal to stabilize, you now can see a display on the picture monitor. And when I misadjust this vacuum guide, you'll notice a very definite jogging or Venetian blind effect, wherein each band in the picture separates in such a way that the timing varies from the top to the bottom of the band. This is the basic error which is developed in the signal whenever the vacuum guide is not set to quite the proper position. We can take that distortion out of the picture by restoring the proper adjustment as I'm now doing. If you take it off in the other direction, of course, the jogs go off in the other direction. That's put it back to the point where the vertical lines in the image are all properly reproduced. Well, we've had time to discuss only a few of the many features and aspects associated with a complex system like the television tape recorder, but I trust that you have some impression as to the physical nature of the machine and some of the functions that it can perform. In practice, these machines are designed so that they can accept a very wide range of accessories. I've commented on the color stabilization circuits that can be added. There are certain other facilities, such as electronic editing facilities, that enable one to achieve the equivalent of a splice in the videotape without actually having to physically cut the tape and join another piece to it. There are also more sophisticated types of servo systems. Arrangements can be made to operate the machine on international scanning standards rather than just the American standards, and so on. But I think what we have shown should have been enough to convince you that the television tape recorder is indeed a good example of the application of the electronic engineer's art.